Hey everybody, I wanted to spend a little bit of time talking to you about how to perform what I like to call a complete interpretation using NMR. Not only proton NMR, but carbon NMR. This should be used in conjunction with, not competition with, Professor Sherlock's notes on how to interpret NMR and how to use NMR when you have a compound. So in the lab, one of the things that we're going to be doing is using NMR to determine structures of compounds. We don't have an NMR at our CBC, but we can definitely get the spectra, and we can interpret that. So let's spend a little time doing a little bit of complete interpretation. Before we get started, we need to know something about chemical shifts. So just so you have an idea, a compound with a proton will show up anywhere in a NMR from 0 parts per million all the way up to, I've never seen anything all the way up to 12, but it can be there. Okay, and so you can see the range here. The most common things are aromatic hydrogens and alkyl hydrogens between about 0.5 and 2. Aromatics here between 7 and 8 usually, and then other special hydrogens that go on here, like aldehyde hydrogens, acid hydrogens, things like that. So I'm sure that you have one of these available to you, but this is one of the things that you're going to need in order to interpret NMR. The next thing that we want to talk about is coupling. Now, coupling happens when protons on adjacent carbons interact with the hydrogen, or the protons that are being read by the NMR. And so the rule is an N+1 rule. Okay, so if you have, for example, this methyl group here has 3 hydrogens on it. Next to it, there are 2 hydrogens, so these will couple to this. So you will see, for this methyl group, you will see a triplet. Okay, meaning that there are 2 hydrogens adjacent to that methyl group. Okay, and now this methylene group, this CH2 here, also sees or is impacted by the environment of the carbons next to it with hydrogens. And so if you see this methyl group here, or not this methylene, this secondary carbon with 2 hydrogens on it, will be impacted here, and you'll see it over here as a quartet, which means that that's not representing 2 hydrogens or 3 hydrogens. It's representing that it is next to a carbon that has 3 hydrogens in it. Okay, so this will be a triplet, and then the integration, the area under the curve, will integrate to 2, meaning there's 2 hydrogens. Okay, so that's how coupling works. It's the N+1 rule, and it's for the adjacent hydrogens. Okay, so now let's look at this methyl group right here. There's 3 hydrogens on it. 1, 2, 3. But those hydrogens are not next to a carbon with any hydrogens on it. So this is a singlet because it's next to a carbon with 0 hydrogens. It's got 0 hydrogens next to it, and then +1. So that means you're going to see a singlet in the NMR. Okay, so that's how coupling works in NMR. You have to look at what's next to it. Now, there are some complex coupling rules. You can have all sorts of crazy things, but I think for lab and for organic chemistry, we're going to try to keep it fairly simple. We're not going to get into like crazy couplings and things like that. Okay, so some examples. Okay, here we have orthoxylene. Okay, so O-xylene. Okay, and so we have this here, which is a singlet. And then we have this here, which is not a singlet, but it's just kind of a messy, junky peak. Okay, so if I'm going to give a complete interpretation of this NMR, okay, I'm going to look at this and I'm going to say, well, this is going to integrate to 3 and this is going to integrate to 2. Okay, well, this information would be given to you. Okay, so here's what I would do. I would say the singlet at 2.3 indicates a methyl group that is attached to a carbon with no hydrogens. So I would say that this is a 1 and a 1. This singlet is that peak in the NMR. Okay, and so I would either write that or indicate that somehow. Okay, and then the next thing would be this peak in the carbon NMR, which is down here in the aromatic hydrogens. Now you'll notice down here that we have 4 aromatic hydrogens on this thing. There are some hydrogens that are next to carbons with hydrogens on them. So this has weird coupling, but aromatics sometimes have weird coupling stuff with them. So what I would suggest is that this peak is the aromatic hydrogens, and that this represents both aromatic hydrogens that are in a unique environment here. And I would write that also. So now what you've done is you've indicated what each peak is, what the integration means for them. This represents 3 hydrogens. Okay, even though there's 6 here, keep in mind that this is a symmetric compound. So you have 3 here and 3 here, and these are chemically equivalent. So that means you're only going to see 1 peak for each of those compounds. So you have a singlet that represents 3 protons in the NMR, and that's the methyl group hanging off of the aromatic ring. And then you have the peak down at just above 7 parts per million, which represents the 4 aromatic hydrogens that are have some sort of weird coupling or strange coupling that's hard to determine. Okay, here's another one. Okay, so this is interesting because this has, again, has coupling that we have to worry about. This is a triplet. Okay, this is a quartet and a triplet and a triplet, and it looks like a singlet. Now this is computer generated, but it still can give us good information. And again, when you're doing this in lab, typically you have a structure that you know that you're trying to make. It's not some willy-nilly like pick one of a billion structures. You can assume it's either going to be the reactants, one of the reactants, or the target product. So you can really narrow down what you have when you're doing this in the lab. Okay, so the first chemical shift that's really easy is this one. Again, this isn't necessarily a singlet, but this represents the aromatic ring. So that peak that integrates to 5, which means 5 hydrogens, represents the aromatic hydrogens on the benzene ring. Now, as we move along here, keep in mind that any electron withdrawing group, like oxygens and carbonyls and any of these groups, will pull the signals downfield, so you're going to have lots of interesting interpretation here. So the first thing is that this that integrates to 3 is a triplet, and that represents this methyl group. Okay, that methyl group is a triplet because, again, when you look at the carbon next to it, there are 2 hydrogens on the carbon next to it, so that means you're going to see 3 peaks, and that's a triplet. And so this one, so that represents this. Okay, and now we look here. Okay, well, what's that? That's a quartet, and that means, again, if it's a quartet, that means that there are 3 hydrogens neighboring on the neighboring carbon. So this can only be one of the peaks. This must be this carbon right here. Okay, because again, if we look next to it, it has 3, so that means it's gonna couple into 4 different peaks. It's a quartet. Okay, so that's 3 of the peaks completely interpreted. Okay, so now what if we go here and we talk about this? Okay, well, this again is going to be a carbon that is next door to a carbon with two hydrogens on it because it's a triplet. Okay, and it integrates for 2. So is it going to be this one or is it going to be that one? Okay, is it going to be this one or is it going to be this one? Well, I would hazard a guess that it's going to be this one because it is the oxygen pulls these hydrogens further downfield. Okay, so that triplet represents that CH2 group. Okay, and then the last one here, this guy, this is again a triplet. So that means it's next door to a carbon with 2 hydrogens on it. So that's going to represent this carbon next to the oxygen, which is pulling it downfield, okay, into the 4s. Okay, oxygen pulls hydrogens down into the 4s because that's its electronegativity. So I would indicate that. I'm not writing it for you, but I'm telling you that when you do a complete interpretation, you should incorporate the integration, the coupling, and the chemical shift in each of the peaks so that we know that you know what you're talking about. Okay, so we can do one for carbon NMR. Carbon NMR is a little more straightforward because there's no coupling in carbon NMR. Carbons don't couple with each other. So I'm sure, again, you have this reference list where you have some selected different types of carbons and where they show up in an NMR. So again, if we have a carbon NMR like this, we are going to decide which peak is which, and we want to, again, completely interpret this. So notice we have 5 carbons in our structure. Okay, I'm going to number these 1, 2, 3, 4, 5. And when we have those 5 carbons in our structure, notice we have 5 carbons in our peak. So this is, again, I'm not going to number them because I don't want to confuse this right now, but okay. And now so each carbon is represented by a peak in the NMR. Now, for a complete interpretation, all we really have to do is decide if it makes sense, if the chemical shift lines up with where they are in the structure. And again, in lab, you'll have structures. You're not asking to create something out of nothing here. Okay, so the thing that I like to do is kind of start down here. What carbon is pulled the furthest downfield? Okay, well, it's this one and this one. Why is it pulled downfield? Well, just like in proton NMR, when you're next to a carbon, it pulls the signal downfield. So this peak right here could be either carbon 3 or carbon 4, but which one is pulled more downfield? This one right here. Okay, it's attached to more stuff. So this peak is going to be carbon 3. Okay, but right next to it is a carbon that is pulled almost as equally downfield. So this is going to be carbon 4. Okay, and so now we have 1, 2, 3 more to worry about. Okay, and notice they're all kind of in the same spot. If we look, we have 1, 2, and carbon number 5, which are kind of all connected to carbons with hydrogens. They're all kind of alkane hydrogens or carbons that just kind of fall in the same spot. But we can still interpret this based on what they're connected to. Okay, so I would say carbon 2 is going to be the one that's pulled the next furthest downfield. It's one carbon away from the oxygen. This one's one carbon away from the oxygen, but it's not in the middle of the compound. It's at the end. So this one being in the middle of the compound, this is going to be carbon number 2. Okay? And that matches what we know about the chemical shift of the carbons. Okay? This area is the alkyl carbon area. So now we have 2 remaining carbons, and again, carbon number 5 is going to be pulled further downfield because it's closer to the oxygen than carbon number 1. So this is going to be carbon number 5, and then this last peak here, the one that is the closest to 0 parts per million, closest to 0 chemical shift, is going to be carbon number 1. Okay, so when I'm asking for full interpretation of an NMR, what I'm hoping is you can correlate all the carbons and all the protons with the structure that you're interested in to verify what the form or what the structure is in the lab. Okay. Again, I think it's a skill to be able to explain this in a way that makes sense so that you are conclusively indicating that the product was made, or maybe the product wasn't made. Okay, so this is what a complete interpretation would entail. And again, I'll let you go about trying to write up what I'm saying. But the idea is you want to make sure you address every peak and apply it to each of the ones in the compound. Okay, and then by doing that, I also think that if you're wrong, it will show up. You'll be able to say, oh my gosh, there's 5 peaks, but I only have 4 different carbons. Or there's, this is a triplet, but it should be a quartet, or this should be a singlet. Maybe I need to go back and look and see if this is really the product. And that happens all the time in interpretation. Okay, so that is the video on interpretation of NMR, and I hope this helps you out. Have a great day, everybody.